In this video, we are going to talk about adders, which are half adders and full adders. So adders is just to add binary numbers together and have a carry, sometimes receive a carry from the previous summation, and then use that carry into that adder to get a result and a carry for the next stage. It's a very fundamental part in the ALU, arithmetic logic unit in the CPU, which is so the role for that one. So for example, adder is part of ALU, that's the ALU. So we have adders, subtractors, multipliers, dividers. So adders is part of ALU, and ALU is part of the CPU, right? Everybody knows what is CPU, since when you are ordering a laptop online, you are looking at the CPU, if the CPU is good enough. So that's the central processing unit, which the heart, the core of the CPU is the ALU. And you have adders, subtractors, and everything else in the ALU to do the computation for the input and output for the computer. Okay, and there are two types of adders we are going to introduce here. So the first one is half adder. So the half adder, why it's called is half, right? Why half? The reason is it's not taking the carries from the previous sum. So if we draw a block, logic block, it looks like this. It only has two binary bits, A, B, and A, this is H, A. So half adder, and you have output, which is the summation, and you have a carry out. That's it. That's a two inputs, two output. So here's the sum, here's the carry. And the truth table for a half adder, we just add these two binary bits together. And you have an S, you have a CO. So we just try all the combinations here, 0, 0, 0, 1, 1, 0, 1, 1. And the summation, 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 is 1, 1 plus 1 is 0, and the carry out is 1. For the rest of them, you don't have any carries, so just put a 0 there. So that's the entire logic truth table for the half adder. So now we just need to design a circuit out of the truth table to implement half adder into the circuit. So now let's take a look at it. It's super simple. We just take a look, since we have two outputs. So that's why we are looking at the two columns one by one. So if we look at S, what's the logic there to make up S? So keep in mind, if you make a SOP, you are looking at ones, right? That's the SOP. So you can have S equals to A not B or A B not. And if you look at this logic function, it is actually a XOR gate. Okay, pretty interesting. So the half adder is actually simply a XOR gate. What about CO? There's only one here, so it's going to be AB. It's just an AND gate. It turns out the circuit for the half adder is super simple. You have A, you have B. So remember, how can you make a S, which is a XOR gate? And XOR gate, XOR gate. And wait, do you have two or one? Or just one? Yeah, XOR. So remember the way how to remember that, how to draw the schematic here. So this arc, external arc, if you have X, so it's going to be X and then OR gate. XOR. And for the carry is an AND gate. So here's S, here's CO. That's the entire circuit for the half adder. If you put this stuff in a black box, it's gonna be an adder for you. Can do that job, the half adder function in the circuit. So after we have half adder, you might be wondering, hey, what is a full adder though? Yeah, actually full adder is being used more often. Sometimes we use a half adder to build up a full adder as well. So the full adder is something you can see everywhere in the modern digital systems. So full adder has 3 inputs, which take care of the carry in from the previous stage. So for example, you have more bits, more stages of the full adder here, 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 and in the front they have several others. So the carry out, for example, you have a carry out here, will be delivered to carry in. This is how you can use a carry from the previous stage as an input for the adder. So you'll need a full adder, S, which is the summation, CO is the carry out. So still 2 outputs, but now you have 3 inputs instead of 2 inputs compared to the half adder. Okay. No, now here's a logic block. That's it. So people, when the customer is asking a computer engineer to build some digital circuit for them, they will let them know the first thing is how many inputs do I have, how many outputs do I have, and then what's the logic or relationship between the input and output, which is a truth table. So keep in mind, what are these steps when you start doing a digital design? It's actually starting from the function block. You know how many inputs, how many outputs, and what are the relationships among all these input outputs, so you can get a truth table, and then you can simplify that and design the logic block out of that logic, and then get a circuit out of it. 0, 0, 0. Since you have 3 inputs right now, so we just explore all these combinations. You should have 8 options. Okay, all these ones. Now let's see. If you have 0, 0, 0, the summation, just add these 3 bits together. You're getting a summation of 0 and no carry, right? And 1, no carry, 1, no carry. Now you have 0 carries 1. 1, no carry, 0 carries 1, 0 carries 1, 1 carry out 1. Okay, that's the entire truth table. So all these previous lectures, we introduced the truth table and how do you write down all these combinations. If you are confused, if you are totally lost here, I recommend you send me an email or refer back to the previous tutorials or lectures, since these ones really lay the groundwork for all this future work here. So you need to probably review that if you are totally lost here. Don't worry about that. You just go back to the videos, you should be able to get it. And we have the truth table. The next step will be, so here's a logic block, input, output, and now here is a truth table, right? So the next step will be what? Kmap, of course. So that's number 1. Should know what is a I/O. Number 2, truth table. Number 3, Kmap. Or is a Kmap? Since you want to start simplifying the logic. So you have 3 inputs. You want to split them up, A and BCI, right, for 2 groups. And A has a chance of 0 and 1, just 2 possibilities. And BCI can be 0, 0, 0, 1, 1, 1, 1, 0. Keep in mind, you're just changing 1 bit for JSON cells here, okay? And now, let's look at S first. So for S, where are the ones? 0, 0, 1, 0, 0, 1, you have a 1. 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So totally 4 ones. And unfortunately, you couldn't group any of them together. So they are all separate ones. Actually, the Kmap is not doing anything for you for this case, but just write down the logic. So now at least you know what are they. So it is A, B not, Ci not, or A not, B not, Ci, or A, B, C, or A not, B, C not. And so what we can do for this, so I found out these two terms have a common part, which is Ci naught. And these two terms have a common term, a common part of Ci. So now we can probably group them together and try to eliminate something, trying to cancel out something. Let's combine these two together first. So we're getting A, B naught, or A not B, Ci naught, or these two, A naught, B naught, or AB, and Ci. Now it becomes pretty interesting because we can find out actually this guy is A. Yeah, let's write it down formally in the formal version. A X or B Ci, and this is XNOR. It's an XNOR logic, and also XNOR is actually an invert of XOR. So it is actually this guy. And why is that? Let's prove it really quick. So what I'm saying is this is this. See if that is true. So let's prove it. So this guy is A not B not AB, right? Bar. So we claim this guy equals to this guy. So we have a bar on the top. So what we want to do is split the bar and change the sign. Split the bar, change the sign, split the bar. Okay. We're not together. And now, what's next? Let's try to do it again. Okay. Split the bar, change the sign. A bar bar, B bar bar, A bar, B bar equals to A bar B, A B bar. And that's just AB, right? And now we expand it. We just use A and A bar or A and B bar. And just expand it, just split it, okay? So it's going to be A bar, or A B bar, or B A bar, or B B bar. See if this guy, so what is this guy equals to? So that's 0, that's 0. So it's finally A B bar or B A bar, which is exactly the same as this one. A bar B or A B bar. Same stuff, right? So we just proved that here, which is A. So that guy is A X nor B, which is A X or B naught. So that's why we can replace it with this. The reason we want to replace that is you can find out it is another XOR logic. If you look at treat this entire thing here as one entity, then it's going to be this thing and Ci, or this thing's inverse version and Ci. So it's actually so this entire thing here XOR Ci. right? And you can just feel free to remove the parentheses. So the final version is A XOR B XOR CI. Pretty interesting. So if you have a full adder, then the summation will be the XOR of all the three inputs. That's a conclusion. All right. And now let's take a look at the carry out, because we have two output for the full adder, the truth table, right? So we are done for the summation already. We know what is that circuit look like. So now let's take a look at the CO. So you have so CO equals to A naught BCI or A B naught CI or A B CI naught or A B C. So that's CO. So it looks not really easy to simplify it, just manually. So sometimes I just want to show you, how when you see something, you cannot simplify it really straightforward. So what you can do is you can use the Kmap. So you have A, B, C, I, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So what you have, the locations you have ones are 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1. So these three guys, and we just want to group these ones together to simplify it. So definitely we can do that, we can do that, we can do that. Okay, so now CO actually is for these two groups, which one is being toggled? So which means that one doesn't matter at all, right? B is toggled. So only CI. So it's going to be A, CI. What about this one? It's A, B, because CI is toggled, right? And then this one, A is toggled, so it only has B, CI left. Okay, and then you simplify this just for one step. You're getting A, B, or A or B, CI. That's the first version. That's the first version you can do, which is the most common version, actually, which is a better version, actually. But somebody also do it like that. They just group these two and these two and leave this guy there. Didn't do anything for it. Now let's see what's going to happen for this one, for this version. So V1, V2. So keep in mind V1 is better, okay? But sometimes people use V2 as well. So V2 is we group these two guys, but leave this one alone. So you are going to get A, B not C. So CO, A, B not CI, A, B not CI, or A, no, or BCI, or A, B. And for this one, the problem will be we have this one, and how can we simplify it? So I think we can have a bar. Let's try it. I'm not sure. Okay. A, B, not CI. Let's put A or A bar inside and B, CI. Because this is just one, right? It's not changing the result. And then we have A, B, not CI or A, B, CI or A, not B, CI or A, B. And let's combine these two. So we are getting A XOR B CI or A B or A B CI. And this part is, this one is just like AB1 or CI. So this is 1, this is 1, so it's just AB, right? So the entire thing here is actually just AB. If we wrap it up to draw a conclusion from here, we know that CO actually equals to A XOR B CI or AB. That's a conclusion. That's the second version. Not really being used that often, but if you see this somewhere, you should know it's a carry out for the full adder. Okay, you just should know that. That's it. And so we have the summation, the S and CL, both available here. So we can draw the circuit for the full adder. So here's the S, right? And let's see if we have A, B, CI. So for the full adder, for the S, it is actually just a 2 XOR gate, right? Another XOR, that's S. So what about CO? You need an AND gate, you need an OR gate, and another AND gate. So it's going to be AB. Right? You want to AND them together first. So that's AB, or A or B. So that's AB, A or B. And CI, you need the AND logic, and then these two, OR them together. So that's CO. So that's a full adder circuit. Yeah, that's the circuit for the full adder. So you need 3 gates here. Well, I got 4 gates here. So AB, A and B, that's AB here, right? A or B, A or B, and A or B and CI. Yeah, that's a circuit for the full adder, 1-bit full adder. Okay. So what I just said is this is a 1-bit full adder. You must be wondering why is it 1 bit? You definitely have 3 bits here to be added up. So we are only looking at A and B. They are 2 bits for the two things, binary numbers to be added up. This one is just a carry. So we are not consider this one as a bit into when you are talking about how many bits of the full adder is. So it is definitely just a 1-bit full adder, right? So people also use, sometimes we have a lot of bits in the computer system. For example, your laptop recently, nowadays they are usually 64 bits. You can imagine that if you want to make addition of 2 binary numbers with 64 bits, you have to have 64 blocks like this for every bit to add them together. So if we draw a block, for example, FA, that's a full adder, and we have here these 2 numbers to be added up, and here's a carry in, and you will get a carry out, right, and an S. And we can combine multiple of these ones together. That's another FA, and another FA, and one more, right, to form a 4-bit adder. So know how these things are being stacked together, stay together to make up a multi-bit adder. and definitely you have everything is a 1-bit adder. So for example, we have A, 3A, 2A, 1A, 0 plus B3, B2, B1, B0. So these two guys are just 4-bit binary numbers. They are 4-bit binary numbers. This plus this. So the way you design a digital system to add them up is doing this, right? So you have all the A's, all the A0, all the A0 and B0 are being added up at the first stage, and then A1, B1 being added up here, A2, B2, A3, B3, right? And you have the initial CI here. After that, you get a summation, you got to carry out. So the carry out is being used as a CI for the next stage. The same thing here. So you can name this one as C0, C1, C2, right? And then you have a C3. And you have a S0, S1, S2, S3. So quick question here. So what's the final result in a binary form from this 4-bit full adder? You need to take the carry into the final result, right? So it's going to be, so if you put all the 4-bit binary numbers together, it's going to be C3, S3, S2, S1, S0 will combine together, make up a 5-bit binary number, including the carry. So that's the final result for this addition operation in the ALU. Okay, this is what you need to know here. And the last thing we want to let you know is using half adders to make up a full adder. Just to show you some of the examples, it's not super critical, but you need to know. So using half adders to make up FA, which is full adder. How to do that? So before we do anything, we need to list all these logic functions for the full adder and half adder. So here S equals to A XOR B. This is what we just got from the conclusion. And A and B is a CO. For FA, S is A XOR B, X XOR CI. CO is A, B. So this time we are going to use this version, the version 2, because we are trying to utilize the XOR logic in the half adder to be used into here. So now, the purpose is actually just to implement this function. You don't even need to know what's the name of that. You just want to implement this function, logic function, using this available logic gate here, which can do this kind of job, and to make it up like this. So now let's see. If you have a half adder, we know a half adder is going to XOR the two inputs and get an output here, which is going to be A XOR B, right? And this one will be A and B. That's the function for the half adder. So now we need this. So we need to XOR the two inputs and XOR another input here. So you can actually do it like that. You can have another half adder, have the output from the summation output from the first half adder as input here, and then you XOR a CI here again. So you are XORing all the 3 digits together by doing this, right? So now you get the S without any problem. You're done for that part, for the full adder, because this is A, this is B. Right, this is how to do it. And now, how can we utilize, how can we make up this one? That's a question. So we have a AB here already, right? We have AND gate already, so we can directly use it. And we need this one, which is actually here. We need this one to AND CI. So actually, this one, the C out here is actually the AND logic for these two inputs. It is exactly this one. Okay, so you got this one here. And now you just need to OR these two together to make up a CO for the full adder. So now we have actually a full adder, but consists of two half adder inside. That's a full adder, right? That's what you need to know. So some of the function logic or some logic blocks we are going to learn can be used to build up another function, logic function block in the future. So this is what you need to know. You can reuse all these blocks you already built up in when you are doing the IC design. You can reuse it, so which can simplify your circuit and which will cause less errors because you are not making up new blocks. You are just trying to reuse something you know is it has been working already. Okay, that's a pretty important strategy, has been used really broadly in digital IC design. All right, so thank you for watching. I'm gonna see you in the next video here.